Discrepancy search combinator is something that you can use when you think that you have a very good value heuristic and you would like to trust even more this value heuristic. So assume you have a good value heuristic and you would like to explore this search tree. The question that I ask you is, this solution then is probably very good because, as you know, we try to discover the first solution on the leftmost branch, we try to make it very good, okay? And for an optimization problem. But do you think that this solution is really less good than this one? Well, what's the difference between this one and this one? The only difference is that here we always took the leftmost branch. I will put it in red. So we always took the leftmost branch, and this is why we think this solution is probably very good heuristically. The only difference between the solution at node 1 and the solution at node 5 is this very first decision. But after this first decision that was to the right, for the rest, we always took the leftmost decision. And so the second best solution in terms of heuristic may be this one. So this one is probably very good. The problem with a classical depth-first search is that we will explore all these intermediate solutions, which may be less promising than this one. And so what we would like to do is explore the solution 5 before the solution 2, 3, and 4, and still use depth-first search. How can we do that? The solution is we should classify the solutions according to the heuristic mistakes that they did. So what I call a heuristic mistake is a right decision. Okay, so if you take a right decision, it means that you do not follow the leftmost solution. And we will call that number the discrepancy. The discrepancy will be the number of right decisions. What I have represented here is the discrepancy of each of the nodes of this search tree. And so the discrepancy of this node is 0 because you always went to the left. The discrepancy of that one is 1. Okay, but as you can see, 5 has also discrepancy 1 because we also have 1 right and then 2 left. So the discrepancy of 5 and 2 are exactly the same. Okay, discrepancy of this one is also 1. Left, right, left. So we do +1 here. Okay, and this is why we have 1. Okay, and so on. And so probably the worst solution is this one, according to the heuristic, because it was always taking the right decision. And so if you trust the decision, you would like to visit the nodes, the solution nodes of the search tree increasingly according to the discrepancy. How can we do that? We can do that with a discrepancy limit on the depth-first search. And the discrepancy limit will be, we want to discard all the branches with a discrepancy that would be larger than this number discrepancy limit. And we will augment this discrepancy limit gradually. Okay, so first we will start a wave with a discrepancy limit of 0, which means that we will only explore the leftmost solution. All the rest is prime. Okay, this is when the discrepancy limit is equal to 0. Then we will set the discrepancy limit equal to 1, and we will also visit this one, this one, this one, but also this one, this one, this one, and also this one, this one, this one. Okay, so this will be the search tree that will be explored when the discrepancy limit is 1. If you augment it once more, the discrepancy limit is 2, and now you will explore this, 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 but also this, 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 but also this one and this one. Okay, and finally, you need a discrepancy limit of 3 to also include that branch because the discrepancy of that node was 3. Okay, so that's the idea. So this search is also complete, okay, because of this for loop that will gradually augment the discrepancy limit. but it will give a higher priority to the node with a smaller discrepancy. The question now is, how can we make this search combinator? We call that a search combinator. You can use it with any type of search, like a first failed strategy, for instance, and it should work. Okay, but you can specify discrepancy limit on top of the first failed strategy, for instance. You will implement this as a practical exercise, as an extension of MiniCP during the practical session. Okay, so this will be the class that you will use. Limited discrepancy branching, and the limited discrepancy branching is taking a branching and a discrepancy limit here in the constructor. Of course, here as instance variable, you will store here the branching supplier and the maximum discrepancy, and you need to implement the get, and this get will be in charge of filtering the decisions that will induce, that would lead to visiting a region of the search tree with a discrepancy that is larger than the specified limit. And the way you should do that is that you should wrap each alternative closures such that a call to that closure would also augment the current discrepancy. And you would do a +0 for the first alternatives, +1 for the second one, and +I for the ith alternatives. And for all the ones that are beyond this limit, you should simply filter them from the branching that has been generated by the branching. Okay, so you will implement this during the practical session. So to summarize what we have seen today, we have seen that for the value heuristic, you could use the bound impact value selector to make the first solution looks good and discover quickly a very good solution in order to prune the branch and bound search tree. We have seen also that phase saving could be used in order to use with higher priority the last value that succeeded during the search tree. Then we have seen different implementation of the first failed principle. Okay, all these ones. And these are all possible translation of the first failed principle for the variable selection. We have seen that we could select the variable with the smallest domain size. We have seen that we could select the one with the largest degree in the constraint network. We could try to estimate the impact in terms of filtering with the impact-based search. We have also studied the activity-based search. Activity was a measure measuring the number of times that a specified variable, the domain of a specified variable was changing. Okay, we would choose first the variable with a high activity. We have seen last conflict. It was a good idea to branch on the variables that led to a failure recently, and a generalization of that one was the conflict ordering search. And these two ones could use a fallback heuristic like the degree or the weighted degree, for instance. And finally, we have seen the discrepancy search combinator, which was an idea to, when you trust very well the value heuristic and the variable heuristic, it's a good idea to combine this with a discrepancy search to visit first the nodes of the search tree with a small discrepancy, because these are the most promising region of the search space according to the value heuristic that we have.